Hey everyone, welcome back to Signal Processing with Paul, and in this video we're going to talk about a super important class of systems called linear time invariant systems, or LTI systems. These are systems that are both linear and time invariant, which are topics we covered in the last two videos, so be sure you know what those things mean first. I'll provide a link in the description if you want to brush up on those topics. Now, recall that linearity refers to a system that behaves the same whether you do addition before or after applying the system, and time invariant says the input-output behavior of this system does not change with time. These two notions allow LTI systems to be characterized by a single function, called its impulse response, which is the output of a system when a special function called an impulse is sent through it. How and why this works is the topic of this video. Now, this is important because knowing the impulse response of an LTI system allows us to then calculate the output of the system for any input. And this is what we mean by the system being characterized by its impulse response. It provides a precise mathematical way of finding the output. This is in part why we talked about linearity and time invariance. Systems that combine these notions are easy to predict. And in addition to prediction, there's an easy way to design an LTI system to produce a desired output when given a certain input, but I'll show this another time. In our stock prediction example, if the prediction system we have was LTI, knowing the system's impulse response would allow us to mathematically predict the future stock price given its past behavior, which is exactly what we want. So for now, let's just say our goal is, given an LTI system H, we want to calculate the output Y of t for a given X of t. So we know the system, we have the system, and we have an input signal. We just want to know what the output is going to be when we put this input in. And to do this, we're going to have to introduce a concept called the impulse response. So let's first talk about impulses. Now, an impulse is a fancy signal that has perfect localization in whatever domain it's in, and is often represented by the Greek letter delta. Incidentally, this is also why it's called a delta function, though technically it isn't a function in the strict sense. By perfect localization, this just really means it has only something going on when the argument is 0 and it's 0 everywhere else. And think of it like a super precise probe that only does something at a single instant and doesn't do anything anywhere else. Lots of things can be represented as delta functions if you just take a moment to think about it. Suppose I want to represent the moment I press the power button on my TV remote. Now, I only press it for a specific moment, so if I was to represent the behavior of this button, it stays kind of at rest until the button's pressed, which is just for a moment, and then it returns to being at rest after. So pressing buttons, any of these sorts of things can be represented really well as delta functions or delta functions of time. But it may be easier to think of an impulse in terms of the function it serves. It allows us to sift through another function and grab its output whenever we want. So here we have a shifted version of the impulse, which has its sort of impulsy action at x equals a, as that's where the argument is 0. And here's another function, f of t. The impulse is defined so that f of a equals the integral over t of delta of t minus a times f of t dt, meaning it sifts through the function f of t and grabs the value we want where the delta is located. So in order to do this, we need to define delta of t as a limiting process of something that gets infinitely tall and infinitely thin, but still has finite area. And it has to have finite area because in general, this integral would be 0. Remember from calculus that the integral over a single point of a function is 0. So it needs to have a lot of area to be able to grab the function when we integrate over it. Now, at this point, you may be wondering why we make a big fuss out of this whole sifting thing. After all, can't we just grab the value of the function directly? Why add an integral and all this other stuff? For now, just roll with it because this will become useful later. And as you'll see, doing this allows us to decouple our function from the independent variable t, which it depends on. So if you look at this integral at the top, what we've done is taken f, which is a function of time, and rewritten it as a function of a different variable, a, which is the shift of the delta. So we basically integrated out the time variable that it's depending on and introduced a new variable. And that'll be really useful here in a second. So here's what the impulse function looks like for different values of delta as we take the limit as delta goes to 0. And this is how the rectangle function is defined. It's basically a box. So here is this delta at 0.5. And as we decrease delta, as we kind of get close to that limit, what you'll see is the area will kind of stay the same, but the width will shrink down. And as a result, the height will get a lot taller. So here is delta equals 0.25, delta equals 0.1, delta equals 0.05, and so on and so forth. You're seeing more and more localization, but still having the same area. Now, suppose we have an LTI system H, and suppose further that we know its impulse response. We know how the system responds when we put an impulse in. What can we then conclude about h of x of t? So knowing the system's impulse response, what can we know about h applied to some arbitrary input? Well, the key insight here is to realize that any function can be thought of and written as a collection of impulses. And remember that impulses are maximally precise, so they're useful for characterizing our system and for analyzing functions. So one of the things we can do is we can write our signal x of t as basically an integral of a lot of different delta functions, each one located at a different value of tau, multiplied by the function value at that point. And what this allows us to do is basically not have our function depend on its independent variable time, t. It's going to depend on a new variable, tau, that we're creating right here for this integral. So when we ask what we can conclude about h of x of t given this, basically what we're going to do is we're going to apply h to both sides, and we're going to see how we can factor this using our assumptions of h being linear and time invariant. So let's see what we can do. Well, first let's notice that if h is linear, it obeys superposition, which basically means that h applied to a sum of inputs is equal to the sum of h applied to each input. And recall that an integral is really just a sum. It's even defined this way as a limit. So just as we can take sums out of a system, we can take integrals out as well. And using linearity, in this case superposition, we can conclude that h of x of t is equal to the integral of h applied to shifted deltas times the function value as well. So here's what we're doing. We're just bringing h inside the integral here and letting the integral come out. So we're kind of swapping the places. The next thing to note is because h is linear, it obeys homogeneity. And remember, homogeneity and superposition, they're both baked into the definition of linearity, which basically means if we're applying h to a function of time times some constant, we can just pull that constant out and apply h to the function of time on its own. So looking what we have up here on the right, what we're passing into h is two things. We're passing the product of a function of time, which is a shifted delta, and we're also applying x of tau. But x of tau for any given tau is a constant. We brought h inside the integral, so for all h cares about, x of tau is a constant. So as a result, what we can do is we can actually pull x of tau out of our system because it's really just a scaling factor. And that's what we're going to do here. We're going to pull x of tau out using homogeneity, and we're going to let h just depend on the shifted version of our delta function. Lastly, remember that h is assumed to be time invariant, which is the ti in LTI, not the wrapper ti. What this means is if we know the output of h for a given input, then we know that if we put a shifted version of that input into the system, we'll just get a shifted version of the output. So as a result, if we know that h of delta of t produces little h of t, then we know that h of delta of t minus tau, some shifted version of the delta, is just going to produce little h of t minus tau, which is the impulse response. So as a result, we can conclude that the result of our system applied to x of t is just the integral from minus infinity to infinity of x of tau, h of t minus tau. Again, what we've done here is just using time invariance here because we know delta of t passed into h gives us h of t, and we know from the time invariance property that if we shift that, we'll get a shifted version of the output. Now, an integral of this form has a special name, and this is called a convolution. And we use this so often, we have a nice shorthand for it. For two functions f and g, the convolution of f and g, which is denoted as f star g, is defined as the integral from minus infinity to infinity of f of t minus tau, g of tau, d tau. And as a result, this is what the output of our system is. The output of our system is y of t equals x convolved with h of t. Now, we use this notation here, f convolved with g of t, to show that the convolution itself depends on time. And you can see this by looking here inside the convolution integral, we actually have h of t. So the convolution depends on time. You may sometimes also see people write it like this, f of t star g of t. Do not do this because this makes it look like the convolution just returns a value. Like if I give you f of t for a given value of t and g of t for a given value of t, you can then calculate what f convolved with g is. This is where people get confused. This is not correct. Convolution takes into signals and it returns a signal. Once you do the convolution, then you can plug in a value of t to get the results, but you need to have the actual signals in there first. It's an operator that takes into signals and returns a new signal. So the key takeaway is this. If we have an LTI system H and we want to find the output y of t for a given input x of t, we need to do two things. The first thing we do is we send an impulse, delta of t, into our system and we record the output h of t. So the first thing we do is record the impulse response. Then to find the output, we just simply do the convolution of our impulse response with our input x. Now, this may sound easy, but this convolution integral can be a bit annoying and time consuming to do. So in the next few videos, we'll show a way of doing this that makes it much easier and faster. But before that, I want to discuss convolution in the real world and show how it's actually used. Now, suppose you're in some cool space and you like the way it sounds. Perhaps it's a cathedral, which were actually designed to have these really nice acoustic properties before people had amplified sound and speakers. You want to make your voice sound like it's in this room, but the problem is it's expensive and time consuming to travel and record inside the space each time. So the question is, can we find a way to only take one recording and use that on any sound to make it sound like it would be in this room? And the answer is actually yes. And the way we do this is we imagine this room as an acoustic processing system, which takes in an input, a dry input signal, and then basically produces a reverberant tail, which is often called a wet signal or an affected signal. When we say dry and wet, what we're literally saying is dry is the input to the system and wet is the output. You often hear this in audio terminology. And we can imagine that my voice that I want to make it sound like it's in this space is also a dry signal. So what engineers do is they take a short burst of noise or take a gun that fires a blank, which actually is really similar to an impulse. And then what you do is you record the output of this room. And with this output, we can then take a dry signal, like my voice recorded in a studio, and place it into this cathedral virtually using what is called a convolution reverb, which is a device that convolves the dry input signal with the recorded impulse response. So this is a plugin called the Fog Convolver, one of my favorite convolution reverbs. And what comes out of here is my voice sounding like it was recorded in the cathedral. And one of the cool things about this is you can find these impulse responses of all sorts of spaces online, and using a convolution reverb, make it sound like you recorded yourself anywhere you want. This is one of many uses of convolution, but this is a very straightforward one that's very obvious because, again, you're using a plugin called a convolution reverb. So thanks for watching, and hopefully by now you understand the importance of LTI systems and convolution. And in the next coming videos, we'll be talking about how to do convolution quickly and efficiently. See you then.